sampling distribution of proportions. Hopefully you've worked the remaining examples on page 60. So let's check your work, see how you did. So part B is asking us to describe the sampling distribution of the proportion. So there's our key phrase. It's asking what does the different p-hats look like when I take samples specifically of size 300. So to give a full answer to this question, we need to first say what statistic we're talking about. Again, they tell us in plain English, we're talking about proportions because we have categorical data. So we're going to use p-hat to denote the proportion in our data. Tilde to give the sampling distribution. They can be modeled by. N, the shape is bell curve or normal distribution. All our different sample proportions should be centered at P, the population proportion, 0.28 as it's been the entire problem. And then the standard error, how much do I expect these p-hats to vary from sample to sample, was the square root of P times 1 minus P over the square root of N. So this is the only way this problem is changing here. Now I have a sample of 300. Again, all of that's under 1 square root, and this by itself is a complete answer to the question. I've stated my statistic, and I've stated what it looks like. I'm talking about p-hats, and I've given the shape, the center, and the spread. Again, I've mentioned that I like to work out the standard error off to the side, just to have handy for later parts of the problem. So standard error of p-hat, if you work that out on your calculator and round it to 4 decimals, I got that to be 0.0259. Again, that part's not required. I'm just going to jot it down for later on. All right. Again, you have to have that entire thing that's in the box for your complete answer here, not just one part of it, but all of it. Next part is asking for probabilities, and specifically it's talking about a random sample of 300. So I'm saying yes, that's what I figured out in part B. I know what random samples of 300 look like, and it wants at least 60 accidents. Okay, so I'm going to first convert the question to probability notation because that is the question. It's asking for a probability. So I'm going to say the probability of X, the number of accidents caused by cell phone usage, is at least 60. That's what I want to find the probability of. And again, this is 60 out of a random sample of 300. And when I'm talking about random samples of 300, I don't know what raw data looks like, but I know what proportions look like. That's what we just worked hard to figure out on part B. What do the proportions from samples of 300 look like? So our next step is going to be to convert our question into proportions. So probability that p-hat, the proportion of my sample, is at least 60 out of a sample size of 300. So I've converted my at least 60 to a proportion, 60 out of 300. If you forget that step, this whole thing is going to be wrong. So, skipping ahead here. So just one more step to work that out. That's like saying p-hat is at least 0.2. All right. Now we're in familiar territory because we said a moment ago the p-hats are normal, so we can use z-scores, normal CDF, all of our normal tools here. So next step is to convert to that standard normal unitless case. So I'm going to switch my notation to z to say now I'm moving on to that standard normal case. And we have that z-score formula. Our observation of interest is 0.2. And the p-hats are centered or have mean of 0.28, and I'm going to divide by, thinking very carefully here, this 0.0259. We found in part B that the spread or variability or standard deviation or standard error, the p-hat, is that 0.0259. So let's work that out on your calculator. Hopefully we're all getting the same z-score here of -3.0888. And just a reminder for consistency in the course, we're going to round everything to 4 decimals. There's nothing magical about that, but again, just so we can be consistent. Now we're good to go. We know how to find probabilities under that standard normal curve. We're going to use our normal CDF. And we want above this value at least 60. So our lower is going to be this z-score. And our upper is going to be whatever your favorite big number is for positive infinity. If you work that out and round it to 4 decimals, I'm getting 0.9990. Again, that's rounded to 4 decimals. All right. Next problem. Same setting here. I want to emphasize we're still talking about a random sample of 300. So again, I'm excited because we worked hard up here to figure out what samples proportions for samples of 300 look like, so I can use that result. And this time it wants between 30 and 40%. This is different from the previous problems. The previous problems I had raw counts. Now it just gives me percentages to start with, or proportions, so I can jump right to that. So converting my question, remember this is asking for a probability, so find the probability, and specifically find the probability that p-hat, I take a sample and I get a proportion for that sample, and that proportion lies somewhere between 0.3 and 0.4. All right. We know that p-hats have a normal distribution, so let's use our normal tools here. We're going to convert each of those values to z-scores. It's nothing challenging when there's 2 of them. You just got to convert both of them. So my observation of interest for the first one is 0.3. I know what random samples of 300 look like. I know they're centered or at 0.28 or have mean of 0.28. And for a sample of 300, we figured out the standard error or the spread was at 0.0259. Notice I'm changing the symbol in the middle from p-hat to z to denote I'm converting everything to z-scores. I'm going to do the same thing for the second observation. So my second observation is 40% or 0.4. I'm going to subtract the same mean, divide by the same standard error. Remember, the order you do this in the numerator is very important. And if you work out those 2 z-scores, you should get 0.7722 on the left for our lower z-score. And for our larger z-score, you should get 4.6332. All right. Again, now that we have 2 z-scores, we want to find the probability of being in that region. We'll let our calculator estimate that area for us, so normal CDF. And the lower this time is 0.7722. The upper 4.6332. Type that in on your calculator and you should get something like 0.2200. If I'm reading my handwriting correctly here. All right. So you've been introduced to the concept of sampling distributions for proportions. Remember, that's for categorical data. And you've seen how that ties easily into all this practice we've been doing with the normal distribution. Before we move on to the next section, I just want to emphasize something that's really important that we've been observing. And let me remind you, the standard error for the mean, when we're talking about quantitative data was the standard deviation for the whole population over square root of n. And when we were working with proportions, we had the standard error for proportions, and we've just done a few of those examples, so it should be fresh on your mind. Standard error for p hat was the square root of p times 1 minus p over n, all under that square root. So we've observed this in a few examples. How does the sample size n affect standard error? And what we're about to write is true for either of these. Notice if we're talking about means, the standard error has a square root of n in the denominator. If we're talking about proportions, the standard error also has a square root of n in the denominator. So as the sample size gets larger, what do we expect to happen with the variability of our statistic? If n's in the denominator gets bigger, we divide something into more pieces, those pieces get smaller. So as n goes up, standard error goes down, and then vice versa. If we have a smaller sample size, then our standard error is going to be bigger, meaning more variability in our statistics. So, i.e., large sample gives us less variability, and which is going to be desirable. We don't want our statistic to vary much from sample to sample. And then on the other hand, if we have a small sample, then we're probably going to see a lot more variability in our statistic. All right, so this concludes the last video on sampling distributions for proportions. In the next section, we're going to move on to confidence intervals for proportion, and you'll see why we needed to talk about all this stuff in the first place.